Howdy and welcome back. So motivation. Before we get into the motivation, let's talk about what a container is, and then I will try to motivate as to why perhaps some iterators are helpful or maybe even could be considered necessary. So a container is going to be an object that holds other objects, and some examples that include would be a linked list, as we've talked about, a standard library vector, and there's other examples such as the trees and graphs that we've recently observed. We can view a container as a sequence of elements with a beginning and an end, which will conventionally be defined as one past the last item. So in our linked list, we had essentially a sequence of items, or I guess a sequence of nodes connected to one another through a pointer. So in this case, the end would be one past the last item. So it would be there. And the beginning would be there at the first element within our sequence. And we'll see here that traversing this sequence is going to be one of the behaviors that an iterator will afford to us. But we haven't started talking about iterators just yet, so don't worry about it. Just here's a sequence of nodes. Likewise, we could have had a sequence of contiguously allocated integer objects. Let's go 1, 2, 3, 4. Then let's go ahead and just consider this one past the last because that is the end of the sequence as it's been defined. So in the case of maybe a vectors array, there's our beginning point and here's our end. And the sequence is going to constitute everything within begin to one less than the end position. Now let's go ahead and, consider this a bit further. Let's consider our common programming task. So a lot of times it's going to be, we're frequently going to collect some sort of data into a container. So if you're reading in, some sort of values, maybe you're creating some sort of object from those values and then throwing them into a standard library vector so that you have a collection of those things, of those entities. Sometimes we might even sort that or organize the data according to some other rule. Frequently, we will want to interact with that data. So we'll retrieve, say, some sort of data item residing within one of our collections. And maybe we do that by index. Maybe we search for it by value, or go ahead and take some subset of our set by a particular property. Moreover, we're probably going to encounter new data, and we might want to add that to our container, or maybe even remove an item that already exists within it. In addition to that, and alluded to a little bit earlier, is that we will need to have some sort of searching functionality to retrieve data, as well as maybe some sort of sorting functionality to organize our data. And then there's obviously some sort of simple numerical operations that can be applied to our data, maybe to derive some descriptive statistics that describe our collection of items. But here's some common programming tasks that can be frequently applied to these containers. And again, kind of think that, okay, there's a sequence of items encapsulated within that container. There's some sort of entry point. Maybe it's a head pointer. Maybe it's a root pointer. Maybe it's the base address as to where something starts. And then there obviously has to be some sort of end to that sequence, which will be dependent on the container we're talking about. So I wanted to go ahead and consider finding an element, and let's just consider what it means to find some particular element within a container. So if we want to search or find an element within a vector or a linked list or otherwise, we're going to need some sort of means of accessing an element. That is actually looking at the element as to where we are kind of in this process and investigating and seeing what it is and whether it is or not what we're looking for. The next thing we're going to need is some sort of ability to compare that element to, what it is we're looking for. Right? And then we're obviously going to need some way to move from one to the next element. And we'll go ahead and say this is would be achieved with some next element operation, whatever that may be. So with all of this in mind, let's think about how we might implement this for an array versus a linked list. And the goal here is going to try to get these two algorithms as close to one another as possible in terms of how they're defined. Just to show you that the process is almost the same for both, and we'll see what that is, but let's go ahead and consider the array version. So I went ahead and said, okay, we're going to take a pointer to the base element of our array. Since arrays do not know their own size, we're going to go ahead and pass in their size, and we'll go ahead and pass by reference to const the value we're searching for. Now, find in this case is going to be pretty simple. For size ti is equal to 0, I is less than size, we're going to go through, hit the loop body, check to see whether the element at the ith location of first is equal to the value that we're looking for. If it is, we will go ahead and return that element by reference to the caller. Otherwise, we'll increment I and continue this process until I becomes greater than or equal to size. In that case, we go ahead and throw a runtime error communicating that, hey, the object you're looking for has not been found. Let's go ahead and contrast this with the linked list version. We're going to pass in, and I'm keeping the naming scheme here similar as we kind of move these together. So I'm going to have first, which is going to be a pointer to a node storing some type of type T, and then I'll go ahead and pass by constant reference the value we're looking for. Now, how this is going to kind of process is, I don't think this is any different from what we've seen to this point in the course when we were interacting with linked list. Essentially, while we're not at the end of a linked list, so while first is not equal to the null pointer, we'll go ahead and check first data to see if it's equal to value. If it is, we're going to return the address of the node storing that object. Otherwise, we'll go ahead and move first to first next. Oops. First to first next. And then if we arrive at the end of the linked list and we did not find that element, we'd go ahead and return null pointer and let the caller figure out what to do in that instance. So here's my first attempt at moving this a bit closer together. So let's go ahead and send in first, last. These are both going to be pointers. First is going to be a pointer to the base element within an array. Last is going to be a pointer to one past the last item within the array. And then const t that we're searching for will be passed by reference to const to this function. And then we're setting this up as well. First is not equal to last. We'll go ahead and dereference first, check if it is equal to the value being sought after. If it is, we'll go ahead and return the address to that object. So that's starting to look a little similar, right? And well, if it's not what we're looking for, go ahead and increment first to move us from the current element under consideration to the subsequent element. So how this looks is we have some sort of array here. First, we'll start out pointing or storing the first element within that array. Last is going to point to the address one past the last indexable element within our array. And then as we're stepping through this, we're searching for some value, we'll move first forward if we do not find a match until we'll continue doing this. Until we either find a match or until first is equal to the last. In that case, we would know we've exhausted our search. Value cannot possibly be in this array because we've checked in every location here. So in that case, we can go ahead and return last and let the caller figure out what to do. So we're on to something here. I mean, looking at this, we're seeing some similarities, but we're not quite there yet. So, I mean, just looking at the parameters here. And I'll go ahead and say that our definition of the linked list version has not changed from the previous version just yet. So we've made one step forward. We've gotten our array find a little bit closer to the linked list implementation, and we're one step closer to a generic algorithm that would be able to find a value within an array or a linked list. But we're not there yet. Okay, so let's go ahead and try to make this even more similar. So I'm going to go ahead and update our definition for the linked list version now. I'll add in a second parameter here. I gotta say third parameter, but it will fall as the second parameter in the parameter list, and it's going to be last. So now here's the idea here. If we have a linked list, first is going to point to the first item, the first node. Last is going to point to one past the last element to follow our kind of definition of what it means to have a sequence. We can then go ahead and do something like find, say, I don't know, let's call it head, no pointer. I don't know, assume we're looking for, I don't know, integer values, and this is like 4, 6. Notice that in this definition, one of the cool things we've just achieved now for both the array version and the linked list version is that we could constrain where we are looking within this data structure. If you knew the address of, say, one past the last element that you wanted to search within, you kind of could be looking within a subsequence of this sequence, which is interesting. That provides some additional functionality that perhaps we didn't consider when we began going through this process. But anyways, let's continue looking at this. So now our while statement is, well, first is not equal to last. Whoa, that's identical to our array version. We'll go ahead and check whether first data is equal to the value under consideration. Well, that's a bit of a deviation from what we're doing in the array version. So we're not quite there yet, but let's continue going through. We have this different way of moving from one element to the next element. And then we have the condition that if we don't find it, we just return last and let the caller deal with that. So now we're like almost there. This behavior is almost identical depending on if we're looking to find something in an array or looking to find something in a linked list. The only differences kind of is how we look at the data. In the case of the array version, we're performing a dereference on that address. In the linked list version, we're having to ask a node for its data. Likewise, what's actually governing the traversal process? The array version is simply pointer arithmetic because each element in an array is adjacent to the next. However, when it comes to our linked list, these nodes are scattered all over dynamic memory. So in order to get to the next one, we can't just perform some sort of offset, but we actually have to follow that next pointer. So the big question is, how can we create a generic algorithm where the definition is identical, accommodate these two very different things? First, the accessing the element. Second, the maintaining a similar traversal process. And at this point, you're probably looking at this going, I don't see an easy way. And that's understandable because what we're going to have to bring into our discussion is a new type of object, which we will see is going to be called kind of a iterator. But here's what we're going for. We want some sort of generic algorithm that will allow us to find a specified value within a collection of elements of that type. So what we have here is we want to maintain this kind of idea of a first and a last, one past the last element. We want to kind of consider a traversal through that sequence. We keep checking to see if we found a match as long as we're not at the last element. We want some consistent way to perform to actually get the value or the data value that from the collection or the container that we'd like to compare to value. And then we definitely want some consistent way to move from one element to the next. So, ideal. It would be ideal if we could write code for common programming tasks such as searching, finding, etc. That does not have to be rewritten every time we come up with a different way to store the data. That is, it'd be cool to have this generic find algorithm that we could apply to vectors, lists, trees, and that is, so we want some sort of universal way to access our data, independent of how it is stored, independent of the underlying type. So here's what we're kind of going for. We want to have algorithms that can manipulate our data, but don't have to know about the underlying structure of the container upon which they're operating. We want containers to store data, but we don't want them to have to know about algorithms. So right here, we're creating this separation of concerns. How we would like them to interact is kind of through an interface of sorts, an intermediary. And we'll go ahead and see here how the next topic, iterators, reliably allows us to do this.